Okay, this is section 2.6, and in this section we're going to learn about the limits at infinity and what happens when you have a horizontal asymptote. So first we're going to start with the definition. Definition says the limit as x approaches a of f of x is equal to infinity means that the value of f of x, of your function, can be made arbitrarily large as we please, by taking x sufficiently close to a but not equal to a. Okay, now remember a is going to be a value for x. So here I have an example where I actually have two examples where they give you the graphical representation of the functions. So here I have two examples, a and b. So here, if we're taking the limit as x approaches a, remember you take the limit from the left and you take the limit from the right. Okay, so here, right underneath this graph, I have the limit from the left. If you take it from the left, it goes to positive infinity. It keeps going up forever and ever, so it goes to positive infinity. Now, if you take the limit from the right hand side, it looks like it keeps going up, so it goes to positive infinity. So therefore, when you're trying to find the limit as x approaches a, in this case, of the function, because the limit from the left and the limit from the right gives you the same value, that will be the limit of the function when x is approaching a from the left and from the right. It goes to the exact same value. Alright, if we look at the next one, we have this way, from the limit from the left, limit from the right, it looks like it's going to the same value. So here I have it again, it's kind of similar to it. It keeps going down both directions, so the limit as x approaches a in this case, in this function, they both keep going down, so that will be negative infinity. And that's what we have here. Okay. Alright, so now we have one more definition that will kind of explain this, exactly what happens, a little better. So it says the line x is equal to a is called a vertical asymptote because of the curve y equals f of x if at least one of the following statement is true. So if you have any of the following ones, then we know that we have a vertical asymptote at a. Okay, so if it goes, the limit is equal to infinity, the limit from the left is equal to infinity, or from the right, or the limit goes to negative infinity, that means from the left and from the right is going to negative infinity. That will tell you right away that the value a will be a vertical asymptote. Okay. Alright, so here we have some examples. Example 2, we have the limit as x approaches 0 from the positive side, from the right side, of ln of x is equal to negative infinity. The line x equals 0 is a vertical asymptote for the y equals ln of x. So if we draw this picture here, I'm going to try to make a little sketch of this. So we know ln of x is going to look something like this. And as you're approaching 0, this is x equals 0, from the right hand side, you are going to go to negative infinity. Okay, so that's what this is saying. So these are just examples. The next one, it says, and I apologize for how small this is. It says the limit as x approaches pi over 2 from the negative side, tangent of x is equal to infinity. Now here we have to remember that for the graph of tangent, we know that we have some vertical asymptotes here. So let me try to make a picture here. This is x. So we know that if this is pi over 2, and this is negative pi over 2, we know that here we have some vertical asymptotes here. I'm just going to put a dotted line. Same here. And if we try to make a sketch of tangent of x, it's going to look something like this. Right? Okay, so now if we take the limit as x approaches pi over 2 from the left hand side, that'll be this side right here. So are you going up this way? It goes to positive infinity. It keeps going up. So that's why it's equal to positive infinity. Okay? Now, if you take it from the right hand side, so if you take the limit as x approaches in pi over 2 from the right hand side of the same function, so now we're here, we're approaching, I'm sorry, negative pi over 2, sorry. So we're approaching this from the right hand side. In this case, the limit is going to go to negative infinity. Okay. Alrighty. So now let's look into another definition. There's a bunch of definitions in this section. So let's go down to the next definition. So on the previous page, we saw that when we have a vertical asymptote, the limit is going to go to infinity as you're approaching that value, okay? So now we're going to look into the definition that says, let f be a function defined on some interval a to infinity. Then we have the limit as x approaches infinity of the function f of x is equal to L, okay? That means that the values of f of x can be made as close to L, and remember L is the limit, okay? Limit. As we like by taking x sufficiently large. Okay, let's look at a picture of this to see what's going on. So notice here, I'm going to write it right here. So the limit xx approaches positive infinity of this function. So as we go to positive infinity, we're going this way. It looks like it's getting closer and closer to this line right here, which is equal to L. So whatever that value, that's going to be your answer. Okay. Same thing here. You can be above this line. As you go to positive infinity, you're still going to go to, sorry, not infinity. You're still going to be getting closer and closer to this line, which is L. And the last case will be if you're going above and below this red line, you're still getting closer and closer to that same value, which is this line right here. So the limit is still going to be equal to L. Alright, and here are more examples of the same thing, but instead of going to positive infinity, now you're going to negative infinity. So this will be the limit as x approaches negative infinity of f of x. You're still equal to L, okay? But now you're going to the negative side, negative values of x. All right, so what does that mean? Line L is called horizontal asymptote of the curve y equals f of x if either one of these cases happens. So the key here that you have to be careful and keep an eye is this is only going to happen when x is approaching positive infinity or negative infinity. Basically, your limit is going to be whatever your horizontal asymptote is, okay? All right, let's look at an example here. Okay, before I move on to example 4, I want to make a little reference here. So suppose we have a graph. This is x, this is y. We have a graph for e to the x. I'm going to try to make a picture of this. E to the x. Okay, so we know that e to the x, the horizontal asymptote for this is y equals 0. So it's basically your the line of the x-axis, right? So we can say that the limit as x approaches negative infinity here, e to the x is equal to 0. Why? Because it keeps getting closer and closer to 0. And that's your limit in that case, which it happens to be the horizontal asymptote as well. Alright, so now let's look at two examples here. We have the limit as x approaches infinity of 1 over x, and the limit as x approaches negative infinity of 1 over x. So let's look at this one. I'm just going to rewrite it here really quick. Approaches infinity, 1 over x, and the limit as x approaches negative infinity, 1 over x. Alright, so let's look at the graphs really quick. So if I make a sketch of this, okay, I'm not really good at drawing, so let's see how it works. Not bad, not bad. Okay, that was bad, but okay, we get the idea. Okay, so the limit as x approaches positive infinity. So as you go to positive infinity, you're going this way. You're getting closer and closer to what value? Well, you're getting closer and closer to the x-axis, which in that case, that's going to be equal to 0. Okay, and that's your limit. Now, for the same function, but now as x approaches negative infinity, so now you're going to the opposite side, this way, you're still getting closer and closer to the x-axis, which it will be 0 again, okay? So remember, let's make a note here. Remember the y equals 0 is a horizontal asymptote for this function, for y equals 1 over x. So that's the main reason why we get 0 in this case, because it's also an asymptote, horizontal asymptote for this graph, okay? All right, now let's look at a theorem. We have two theorems on the next page. This is a cool theorem. It says if n is a positive integer, then we have this. So the limit as x approaches infinity of 1 over x to the n. Now this exponent is what has to be a positive integer, okay? Is equal to 0. Because remember, if you have a negative exponent on the denominator, then you can rewrite it on the numerator, okay? So this has to be positive. Same case, same thing happens when the limit as x approaches negative infinity of 1 over x to the n, you will still get 0. Okay, so this is a theorem, it's given. We know that happens for sure. Okay, I'm trying to box this and I'm doing a horrible job, but you get the idea. All right, let's look at one more example. We have to evaluate the limit as x approaches infinity of this rational expression. I'm going to try to look at what's going on each of these functions. So if I try to take the limit of just the numerator as x approaches infinity, I just want to look at what's going on here. What is that equal to? Well, this is a parabola, and as x approaches infinity, let me fix my infinity, it's horrible. Okay, I'm not doing a good job. Okay, that's not better, but oh well. Okay, so this is a parabola. As x approaches infinity, you know, parabola looks like a U, it's going to go up to infinity. Okay? Now let me look at the denominator. Denominator, I'm still approaching infinity, and it looks like I have another parabola. So that's going to give me infinity as well. Okay? Now, when you have this special case, the first thing you have to keep an eye is make sure x approaches infinity. Okay, I'm going to put exclamation marks here. So keep an eye on that. The next thing you have to do when you have something like this going on, look at the exponents or the leading exponent here. So when you have the same exponent, here, the highest same exponent, you can rewrite this just by using like x squared over 3x squared. And then you can simplify this. Okay, that's supposed to be a square. There you go. Then you can simplify here. So I get the limit as x approaches infinity of 1/3. Now this is a constant. The limit is going to be just 1/3. And that's it. Okay? So you can only do this when you have the same exponent. So just because I have x squared over x squared, I can do this. So you can do that every time, okay? Now I'm going to give you an example of something else. So here I have a new example. This is not in your notes. We're going to call this the bonus example. This example is included in your class. It's free. It's part of your class. Okay, so now I have a different case here. I have a parabola here. This is to the third power. They're not the same. I can't do just look at the coefficients and that will be my limit. But I can still simplify and play around with this. I can still do this. I can still take this too and be like, hey, I can simplify this. And you will have the limit as x approaches infinity, and we're just simplifying the exponents here. So I will have 3/2 x. Now if I take the limit of this is a linear equation. It's a straight line. So as you go to infinity, when you're trying to take the limit, the line is going to keep going, right? And it's a positive slope, so it's going to go up forever and ever. So the limit is going to be infinity in this case. All right, I will cover the rest of the section in class. So thank you for watching the video.